So I hope the friends will join. Okay. So in the meantime, if you have any question in doubt, you can ask. Okay. Teza, no sir. Any question after the last class?
No, sir.
No, sir.
Okay. So you have understood how to draw your displacement diagram, velocity diagram, and acceleration diagram for different types of motion of the folder, right? So we have discussed about assets and motion. Okay. So after that, initially we have discussed about the uniform velocity case. Okay. And later on, we have gone for your assets and motion of the folder. Okay. That is one of the standard motion that we have discussed. Okay. And there we have seen how to draw the displacement diagram, your velocity diagram and acceleration diagram for different cases. Okay. So now, is my screen visible? Just let me know.
Yes, sir.
Okay. So if you recall in the last class, okay, so we have discussed about how to draw the displacement diagram in the case of a system. Okay. So there we have seen that basically like this theta a, this extends stroke angle, dual, stroke angle, next dual, etc. Those things as per scale we have to mark on the x-axis and considering the leaves, okay, y-axis, long y-axis, we have to consider the particular leaf, and once again as per scale we have to draw this. We have to complete this rectangle, then as per whatever is the theta a, delta one, dual one, delta theta d, etc. Okay, we have to complete those pixel boxes. Okay, so this rectangle. And after that, as it is a system that we are talking about, so now considering this leaf as the diameter, okay, we have to draw the semicircle here. Okay, so this semicircle is being done, and now our task is to basically we are going to divide this essence stroke, etc. Okay, and that will be corresponding to how many divisions you make in this particular semicircle. Okay, so as to make it project the assets and motion here. Okay. So now for that case we have to, if you recall, and even number of division equal space division we have to go for. So minimum 6 division we go, we can go for 8, 10, etc. But that will give you better accuracy, but time consumption will be more. So 6 is kind of optimum. So 6 division we are making here. So correspondingly, theta A as well as theta B we have 6 division. And how we have located those points. So first, then we have drawn those from this circle, okay, wherever it meets, wherever they start, okay, those division. So from there we are drawing the horizontal lines, okay, and the first line along with the first vertical, wherever they meet, that is the first point. Similarly, second horizontal line along with the second vertical line, this is the second point, and so on, okay. And after that, with a smooth curve, okay, we have closed line. And once again, in the case of dual, there will not be any motion of the follower, so no displacement of the follower. Follower remains stationary there in this place. So this way we have to darken here. And after that, return to the follow cycle. Okay. So already on diagram, installation diagram was going to discuss. And after that, we have discussed about the uniform acceleration and uniform direction case, where we have seen once again here also on this theta A, theta D, dual, etc. And so on, the part scale to consider, and along the y-axis you have to consider the lift of the follower. Once again as per the total scale, okay, that is the, and after that making those division of for theta A, theta F stroke, dual stroke, theta return stroke, etc. That has to be done, and once again we will make some different equal space different number of division in the theta A as well as theta D. Okay, right now we are on 7.6 division. After that, like the middle vertical line we have to consider, and if you have made 6 division here also in the vertically you have to mark 6 equally spaced division. Okay, so like this B, C, D, E, F, G, those things you can see. And how to locate now the point and draw the curve. So now for its uniform equation in the first half, uniform equation in the second half. Okay, so for the first half, okay, so you start from this point or this point, okay, and you are going to join this origin with this particular whatever is the location we are going for here. Okay, so then we see those divisions. So first one first, okay, now we are going second, third, and so on. And for the other half, we start from here. Okay, and now for locating the point, once again just like the first line, first of this line, and first vertical is considered wherever they intersect, that is the point. Similarly, second oblique line and second vertical, wherever they intersect, that is the point, and so on. And after that, you have to join them with a free form curve. Okay, so this is how it happens. So those things already we have discussed. Similarly, how to draw the velocity and acceleration diagram, that also we have discussed. So for velocity diagram, you remember? Yes or no? So this is for once again theta along your consider theta along your this, okay, and velocity v along y-axis, okay. So now in that particular case, so from here to here, this is basically I have to project those angles, okay, and this is nothing but theta a. Similarly, if you project from the displacement diagram, okay, then you will get corresponding dual as well as theta a, okay. So now I'm also from the theta a, okay. So now this is momentum acceleration and this from this. So up to the mid of this, so this is from the accelerator. So this will be just like this. Okay, after that, so coming back like after that there is one of the particular color, so this state will be 0, and after that similar case, but in the opposite direction, so as to show the direction of movement of the follower is okay. Now for the acceleration diagram, theta along x-axis once again, okay, and the acceleration along your y-axis, okay. So now to show it, so it's easy from acceleration, easy from here. So from here to here, once again, if you project, so this much is, because actually this is the your which one, theta a, right? So now in that particular case, so it is changing from acceleration and from acceleration that we are talking about. Okay, so this is right up to this one. Okay, this is from acceleration and third part of it. Okay, in the opposite direction to so this is the different. Okay, after that what it comes back to is next during there is this particular color. Once again acceleration also is 0, and next part that is for your return stroke, okay, it will follow in the, okay. So this is how now like after this much, is it clear? Let me know if there is any confusion. Okay, so now I have shown the how to get that particular expression for maximum velocity and acceleration for this particular case. Okay, and this already we have discussed. Okay, so now you can get some expression. So this expression will be helpful. You can directly apply it. So this is a suffix a. This is for your second stroke. Okay, so VA is equal to 2x omega divided by the a. Okay, where x is nothing but the lead. Okay, omega is what angular velocity. Okay, and this theta is the angle in stroke. Okay, now similar expression is valid for the return stroke also, but the thing is what you have to do, you have to replace theta a with theta b. Okay, so already from the velocity cycle we have seen maximum velocity occurs at half of the time of displacement during the stroke, that is p equal to pa by 2, that is how when we get maximum velocity, right? Yes or no? Now, if we put thing, okay, now we can get the acceleration method, you can say expression for acceleration by doing dp. Okay, we already know acceleration is nothing but rate of change of your velocity. Okay, that is dp. Okay, now velocity, what's the velocity? So maximum velocity is this, and dv is change in velocity is nothing but pa minus 0. Okay, and dp is the half. Okay, and if you put that, what we will get the expression for maximum acceleration. Okay, and that is 4 omega square x divided by theta a square. This is for ascent stroke or the rise stroke. Similar expression is valid for return stroke also. Okay, but we have to replace theta a with theta b. Okay, and this particular uniform acceleration and retardation scheme of motion of the follower is basically valid up to a moderate speed of wind. Previously, we have seen some slower speed of engine only those etc. are replicable, etc. Now with this scheme, you can go for up to a somewhat higher level. Okay, is it clear? Yes. I have it. Yes. Okay. Now, next scheme of motion center one that we have to discuss is the cycloidal motion profile. Okay. So, if you recall from your previous classes, engineering drawing, etc., you know that cycle is a kind of curve that is traced by a point on a circle, and when you consider that where this circle is rolling without moving on a particular straight. Okay. This is how we can have the inference of the cycle. Okay. So now we know that this particular case, if you consider a normal follower to be cam and the supporting kind of follower, so the follower is having a kind of linear motion. Okay. So now that means in case of cams, what happens? The straight line is the stroke of the follower. Whatever that straight line we are talking about, that is for cycloid. Okay, it's a curve traced by a point on a circle. The cycle rolls without slipping on a straight line. The straight line we are going to assume as if the follower motion, linear motion of the follower that we are getting. Okay, so that straight line is the stroke of that particular follower, and the circumference of the rolling circle is equal to the stroke of that particular follower. Okay, so from there, what we will get? So it means if the circumference is the x, so that is a stroke, then we can write 2 pi r equal to x. From there, the radius of that particular rolling circle will get as x by 2 pi. Okay, so r equal to x by 2 pi. So the radius of the rolling circle will be how much? X by 2 pi. Okay, understood? Let me know. No one is responding anything. Yes, sir. Okay. So now we have to see how we have to draw the displacement and the velocity and the acceleration diagram for your cycloidal motion profile. Okay, so now if you follow two different rules, okay, you may see somewhat different approaches for drawing the displacement diagram. But the main thing is you must understand how to draw the displacement diagram because whenever in the next classes, subsequent classes, whenever you are going to design cam profile, then basically the cam profile design will come from, okay, will be the displacement diagram for that particular situation will be very, very important because that displacement diagram will give you the indication about how much like how much displacement that is there during a certain movement of that particular cam, okay, that is cam angular rotation versus the displacement but the lift of the follower it is going to give. Okay, and from there what we will get, we will get an idea that means from the central position of center of movement of that particular center of rotation of that particular cam, what is the location of that particular follower. Okay, and now we know that basically the follower is always in contact with that particular cam, okay, or that is the cam profile, or you can say the working surface of the cam center. Okay, so now if that is happening, so from the lift we know that if this much is the kind of lift, that means this is where our follower is. Okay, and if I know this is where my follower is at a particular angular motion of that particular cam, then I know what is the shape of that particular, because we know that the follower is in constant contact with the cam. So at that location, that is follower is in contact with the cam. Okay. Similarly, if you rotate go for different location and all, okay, if you know what is the lift, that means you know the position of the follower. Now from the position of the follower, you know that follower is in now contact with the cam. That means there itself at the end of the follower, the profile of the cam. Okay. So this is how if you can connect all the dots, basically you are going to obtain that particular. Okay. Yes. Should I move ahead? Okay, sir. Okay. Others? What about others? Yes, sir. Okay. So now we are going to see how we need to draw the displacement diagram. Okay. So for drawing displacement diagram, once again we know that basically along x-axis we have what? Along x-axis. For drawing displacement diagram, what we consider along x-axis? What is the term? No one? For so many days we have been discussing this. If you don't know what is the parameter that we consider along x-axis and along y-axis for drawing displacement diagram, then it will be very difficult. So along x-axis we consider theta. Theta is what? Cam angular displacement. Okay. So now in this particular case we are doing or we are showing drawing the displacement diagram only for outstroke. Okay. Next after outstroke we'll be having the if you consider you will have the dual, you can in the dual there will not be any motion, so you can consider like that. After that it will be similar kind of motion but in the opposite direction. Understood? So that's why here we are just showing the displacement diagram for outstroke only. Okay. Or if you want you can go for the whole thing. Okay. So now for drawing that, we have seen that basically the radius of the rolling circle that is going to be x by 2 pi. Okay. So now if I consider, suppose from here I am going to draw. Okay. So this is the resolution. Suppose this consider this is the projection. Okay. Now considering it as a center, I am going to draw a circle of radius how much? X by 2 pi. Already we have said since why we go for x by 2 pi as the response because we are talking about cycloidal motion. Okay, and now this particular circle we are going to divide in any number of equal parts. Okay, so we can go for 6, 8, 10, 12 like that. Okay, now we are let's consider we are dividing it in 8 parts. Okay, so using protector you can already know that this is the 360 degrees. So where it will be what is the division? That is one division is going to consist of how much? 45 degrees, right? 45, 45, 45, 45, 45, 45, like that. And we'll have 8 equally spaced divisions. So let's consider. So right now we are not drawing like this. Okay, directly we are sorry. We are not showing the division something like this or like this, just like we have done in the previous cases, but we are just marking the points there. Okay, so and this suppose if this is the location, then this is one dash. Okay, similarly two dash exactly vertical. Okay, three dash, four dash, five dash, six dash, seven dash, and 8 decimal. Okay, so 80. Now this is equals, okay, what we are going to do. So from this point we are going to project it on this particular vertical diagonal. Okay, so this is where we are going to project. So now from one we are projecting like this. Okay. Okay. So two from two it automatically becomes this. Three it becomes this. 4 from 4 it becomes this, from 5 it becomes this, 6 already here now. Okay, so just like 2 is already there on the vertical. Okay, so 6 already here. Okay, so this one this. Okay, 7 this. Okay, from 8 this. Okay, and once again from 1. Okay, so these are the. Okay, up to this much is it okay? Is that okay? Let me know. Now this projection or actually on the particle central line already we have done. Okay, and we are naming the points also. Now let's start. Now we have made 8 division here equal space. So now already this theta a, right now we are saying that we are only drawing for theta a. This is the which stroke? Cathode stroke. Okay, so now we are going to make same equally spaced division, 8 division here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, understood? Okay, so 8 divisions we have made here. So 8 divisions we have also made here. Okay, on the axis stroke. Now from this equally spaced division, we are going to draw the vertical lines. Okay, so this vertical line from second division to from third division, from fourth, fifth, sixth, etc. Like that. Okay, we 6, 7, and 8. Okay, and this height is how much? Along y-axis, we have to consider the leaf or the displacement. Okay, and you can close this pencil completely. All of you try to draw along with me, then it will be helpful for you. Are you following me? So while drawing this, as this is practical method, you have to be careful. Your scale is very important. Okay, so proper scale is very important, and using the geometrical instrument, all the scale, pencil, and all those things is important. Okay, right now with this proper scale, I don't mean that using the plastic scale or this kind of thing. Okay, we are talking about what is the like conversion factor that we are talking about. Let's consider theta we are drawing in the x-axis. Okay, so but that is in terms of some length. Okay, so the angle is in terms of length. So we have to write suppose 1 centimeter denotes 20 degrees or something like that. Whatever is your scale. Okay. So up to this part, I hope it's clear. Yes. So we have done up to this. Okay. Now, what we are going to do, we are going to draw the diagram. Okay. From center point of the particular circle, we are going to draw the diagram along. Okay, and from all the other points wherever we have already projected here, okay, on the vertical diagonal. Okay, so vertical diagonal diameter, okay, of this particular circle, from this point we are going to draw parallel lines parallel to the. So already these points, some of the points are same. Only same means we're talking about suppose 6. For 6th division, this is the point. Okay, 5th division we are projecting here. Similarly, for the 7th division also, the projection comes here, the same point. Okay, so from the same point, that is in this line itself, we have to go for the like fifth. Okay, fifth point as well as 7th point. So that will be intersecting in this line. Okay, similarly, this 8th number division is projected here, and this center has become the center. Okay, and fourth one. So that means here in this line, that is this diagonal, okay, on the fourth vertical as well as eighth vertical, the 2 points will be intersecting points in there. Similarly, those from 1 and 3 dash, 1 dash and 3 dash, we have projected at this particular point L. Okay, so from L also we are going to draw this particular line parallel to the diagonal. Similarly, for 2 dash point, that itself was here on the vertical. Okay, so from here we are going to draw. Okay, understood? Up to this part, is it clear? Let me know. Reza, Nohasol, Rehal, Termiki, Nasisman. What about others? Only Rehan is here in the
Yes, sir.
group. Other? Termiki, Asisman.
Yes, sir.
Okay, so all of you are
Yes,
following
sir.
it?
Yes, sir.
Okay. Okay, thank you. So that is done. Okay. So
Yes, sir.
now, okay, now our task is to we need to actually get those points, point of interest, and by connecting them, get that particular curve. Okay. So now, how many divisions we have made on the circle? 8 divisions, right? 8 equally spaced divisions. Okay. Correspondingly, in the theta, how many divisions we have made?
Eight.
Also correct, 8 division only. Okay, so these vertical lines for the division line, okay, for theta division we have made. Okay, so from that 1 dash, 2 dash, 3 dash, 4 dash, etc., which has been the equally spaced division for the circle. Okay, from there we have projected lines on this vertical diagonal of this particular circle. Okay, so we have looked at this points like E dash, L, O, M, 6, etc. So these are the points, okay, along this line. Okay, and from there, after that, we have drawn this particular diagonal, okay, that goes from starting from the center of this particular circle, and this is the diagonal of this particular this portion, theta portion. Okay, the rectangle that is inside the diagonal. Okay, and after that, whatever be the projected points or the different divisions on the vertical diagonal here on this particular circle. So from there, what we have done, we are going to draw parallel lines to this particular diagonal. Okay, so that's why if you start from one, okay, then one has been projected here in this point L. Okay, so from here we have drawn parallel to the diagonal. First two, this itself is projected on this particular line. So from two, it is from here. Okay. From three, once again, whenever we have projected, it becomes the same point. It is L only. Okay. So it becomes the same point. So it's done. From four dash, this is F4. Okay. Already from O, already this is done. Okay. This diagonal is already done. So it is done. From 5 dash, when we have projected, it is the point M. So from point M, we have drawn this particular line parallel to this diagonal. From 6 dash, 6 dash itself is here in this particular diagonal. So from here, once again, we are drawing line which is parallel to your the previous diagonal. From 7 dash, once again, when we have projected, it is the same point M as that of 5 dash point. So this is the same line. Okay. Once again, 8 dash, once again, it has been projected at O, similar to 4 dash. Okay, same line. Done. Now we are going to look at the points. Okay, so for the first case, there is the problem. This itself is the point. Okay, for the second, okay, we are going to see the different lines which have been drawn from the positive side. So from one dash, if I consider one dash, so this was this L is the point, okay, positive point. So and this is the if you look from the below, okay, the second line is the line, okay, corresponding to one dash. And this is the first vertical for first division, okay. So first line corresponding first point and the first vertical they meet here. Okay, so this is the now for the second one, if you see this is the two dash point, and we have drawn the this lowermost one. Okay, this line, and this is the second vertical. So wherever they meet, this is the point. This is the actual vertical. For for locating the third one, once again three dash point is here, and when we have projected, this is this particular point. So this is the second line. So on this line, we have to see. So this line intersecting with the third vertical. So here on this, this is the point. Okay. So similarly for fourth, this is the fourth dash point. Okay. Corresponding line was this. Okay. This line, the diagonal line, and this is the fourth vertical. So wherever they meet, so this is the point. Similarly for the fifth dash, this is the line. Okay. Second line from the top. Okay. And this is the fifth vertical. Okay. So wherever they meet, this is the point. Similarly, for sixth one, this is the topmost one, okay, and sixth vertical, we have to consider wherever they meet, okay, this is somewhere here, okay. So similarly, seven dash, okay, once again goes from 5 dash, this line on the second line, so in here, similar is this case, okay. So after that, what we have to do with a smooth line, we are joining them, okay, and we are getting them, okay. So this is how we draw. Is it clear? Let me know.
Yes, sir.
So So similarly, by for velocity diagram and your acceleration diagram, you can go for theta here. Okay, theta x-axis, velocity and acceleration correspondingly, or respectively along y-axis. Okay, and see what is the we should look at what is the profile, how does it become. Okay, so now mathematically if we see, so what we get, velocity, maximum velocity we get as half of the slope. Okay, theta equal to theta by 2. So this simplification I have already given. So just you can just go to alien can go to right now we are interested in the image. So maximum velocity we get as theta a by 2, and what is the expression for maximum velocity? It's very important. X by theta a into 2 omega, where x is the lift, okay, omega is the angular velocity, and omega is the angular velocity, theta a is the essence stroke angle, okay, and this gives you the maximum, and where it is maximum at theta a by 2, okay, and similarly for return stroke if we talk about, then theta a can be replaced by theta d and you can get the maximum velocity expression, okay. So now that two theta, it is only we are going for theta a only, right? Theta a only. Okay, so that half of it is theta maximum. Similarly, from once you know about velocity, the VDC gives you acceleration. Okay, and by doing that, what we have obtained is a curve, and where we get the maximum acceleration at theta a by 4. Okay, and by doing that on the expression, whatever we have obtained by doing the dt, okay, so we get max, that is the maximum acceleration in meter stroke f, omega square x into t phi divided by theta a square. This is for the acceleration. Okay, and like okay, maximum, okay, maximum acceleration in acceleration. If you want in descent stroke, similar expression is valid, but you have to replace theta a with theta b. Okay, so now here you can see if you look properly, then basically there is no abrupt change in the velocity and acceleration at any of the stages. So if you look here, okay, so these are smooth curves. Okay, there is no abrupt change in velocity and acceleration. So maximum velocity you are getting at theta a by 4. This is the max state. Okay, and for acceleration, okay, it was smoothly decreases. Okay, so it's kind of smooth curve. Okay, similar is the case here. Okay, so this can be also be done obtained experimentally also. Okay, so now you can see there is no abrupt changes. So this particular motion of velocity, that is cycloidal profile, okay, we can go for high speed of engine. Okay, so because there is no sudden changes and all, if there is sudden changes in acceleration, velocity, etc., so some dynamic characteristics that that comes into picture, okay, and the dynamic behavior becomes difficult. Okay, as well as there is like some jerking, all this other impact force, etc., comes into picture. That's why you cannot go for higher speed in the previous case. Okay, but right now it's a smooth curve for velocity, acceleration, etc. that we are going for getting. Okay, we can go for higher velocity, higher energy. Okay, so this will stop here for today. In the next class, we will discuss how to draw the camp profile, and we'll try solving different problems and we'll design camp. Okay, camp profile based on different whatever is the requirement. Okay, so with this, we'll stop here for today. If you have any confusion, you can ask. Okay, any confusion, anyone? Because ultimately these things will be required while drawing the cam profile. This how to draw the displacement diagram for different motion, that will be important, because in the question it will be given, suppose your follower is rotating with this kind of speed, okay, this kind of speed for this angle and all. So those values will get, suppose theta a, dual, theta b, etc. Okay, but you should be able to draw uh, if suppose in this particular SM stock it is moving with SHM, so for SHM, how to draw the displacement diagram, etc. So these things if you know, then from there actually the next step of drawing the cam profile starts. Okay, that's why there will be two distinct stages. One is drawing the displacement diagram properly, and accordingly from the displacement diagram you need to draw the cam profile. Okay, So those things we'll discuss in the next class. So for today we'll stop here. Just let me know if you have understood the thing. If there is any question, you can ask. Done. So then respond to your name calls. Nilotpal. Nilotpal absent. Shankar.
Present, sir.
Then Harsisman.
Present, sir.
Rehan.
Present, sir.
Kathor. Kathor. Absent. Rishikesh Basumatari. Rishikesh Basumatari. Absent. Permiki.
Present,
Permiki.
sir.
Nausal.
Yes, sir. Yes, sir.
Present, sir.
Heza.
Yes, sir.
Rishikesh Nath. Rishikesh Nath. Absent. Emil. Emil. Absent. Okay. So stop here. Thank you everyone for joining.
Thank you, sir.
Thank you, sir.
Thank you, sir.